In calculus, we'll be working with many different types of functions. One of the major things we'll be interested in is how these functions change. Fortunately, this idea is very intuitive, and you may have started to do this already in previous math courses. Let's take a look at a quick example to see how we do this. If we read a function from left to right, we can see that sometimes it increases and other times it decreases. I like to imagine the function as a roller coaster so that I can easily see places where it is going up versus where it is going down. Knowing how a function increases and decreases certainly tells us more about the behaviors of a function, but it's still not precise enough for what we will need later. To see why, let's look at two more functions. Here are two functions that are both increasing, but one is increasing more rapidly. After all, it looks steeper. But how steep is it? Where does it increase the most? From these questions, you can see we need some way to describe how rapidly the function is increasing or decreasing, so we can better compare their behavior. So let's take a step back. If these two functions were lines, this would be a much easier problem. When we are working with lines, we can use the notion of slope to accurately describe how quickly a line is increasing or decreasing. This comes from measuring the rise of the function in the y direction versus the run of the function in the x direction. With slope, we can say how much it is increasing or decreasing by simply giving this ratio of numbers. So we can say that the line on the right is increasing more simply because it has a larger value for its slope. Now back to our functions. These functions are definitely not lines. So unfortunately, we can't use the idea of slope to describe how they're changing. Or can we? To build a line, all we need are 2 points. If we choose 2 points on our function, then we can certainly draw a line right through them. Note how the line works as a good approximation when describing how the function is changing. If the line we draw is steep, then we can expect that our function is increasing fairly quickly as well. But it's only an approximation right now. If we change the 2 points we are using, we will get a different value for the slope of the line. What this line really tells us then is the average change of the function. How much the function has changed in the y direction versus the x direction between the two given points. Let's play around with this idea so that it makes a bit more sense. Suppose we choose 2 points on a function. Drawing our line like earlier, we can find it has a slope of 2/3. This tells us that as we are moving on the function between the 2 points, we may go up, we may go down, but on average we'll increase in the y direction by 2 as we move in the x direction by 3. Or maybe a better way to say this is the average change of the function between the 2 points is also 2/3. If we choose 2 other points, our line is now horizontal. This has a slope of 0. If we move along the function now, you'll notice that despite the ups and downs, we'll end up at the other point at the same y value. So on average, there is no change in the function. So by describing the slope of a line between 2 points on a function, we can get a lot of information about the behavior, specifically its average rate of change. Depending on what the function describes, this could give us information like the average speed of a car or the average flow rate from a tank of water. The possibilities are endless. But that's not all we can do. Next, you'll see how we can use this average rate of change to describe how a function is changing at a single point rather than between 2 points. And along the way, we'll pick up our first major tool of calculus, the limit. Thanks for watching.
I like you, Mary. I like you a lot.
You can't go in there! It's okay! I'm a limo driver!
Man, you are one pathetic loser. No offense. I gotta stop and go to the bathroom.
Just go, man! Oh, that sure is warm.
Hurt me, don't hurt me no more. What is love? Groovy on a Sunday afternoon.